Okay guys, so second video, we will begin with starting to kind of clarify the idea of this degrees of freedom. Not really what they are, but more why we need them and where we would need them. So we're going to actually address that when we're looking for that T critical value. So in order to find your T critical value, well, actually, first let's make the connection between what we know. So we had been finding a Z critical value, and the way that we found that was we were always doing our inverse norm. And what we were inverse norming, if it was, let's say, a 95% confidence interval, was we were inverse norming the area that we were talking about. So we were talking about half of that leftover space. So whatever we got here was what we inverse normed, and then that was giving us our Z critical value. Okay, so with our T critical value, it's very, very similar. But the problem is we're obviously not going to use inverse norm because inverse norm suggests that it's a normal distribution, and we don't have a normal distribution. We have a T distribution. So in order for us to find our T critical value, we're actually going to use inverse T. So it's probably suggested that you have a calculator in front of you for this video, at least for the beginning part of the video, so you can see what I am talking about. You can pause right now to go get it. So under your distor button, which is where all your distributions are, if you go down to the fourth one, you will see that it says inverse T. Okay, so there is a very much a connection with what you can put into your calculator for your T critical value with what you put in for your Z critical value. So if I said to you that it was a 95% confidence interval, okay, you would still do the 1 minus the 0.95 divided by your 2. So you're going to you're talking about an area under the curve that's found by doing that. So 1 minus your confidence level divided by 2 is your area. So that's the one part that's going under your inverse T. Okay, so that's your area. And then alongside that is going to be your degrees of freedom, which would mean that you'd have to know your sample size and subtracting it by 1. This is just a screenshot of, in the calculator, what to put in. These examples may not match anything that we do, but just so that you understand. So the area under the curve here, 0.025, and 11 would be your degrees of freedom. That would mean that you have a sample size of 12. So here is your area of 0.05. Your degrees of freedom here would be 47. That means your sample size here is 48. Okay, you'll catch on real quickly with these two examples. So let's suppose that we have to find our critical value T when we're doing a 96% confidence interval based on a random sample of 22 observations, okay? So in order for us to do that, I need to know the area that I'm talking about. So 1 minus 0.96 over 2, the area under the curve here is 0.02. I also need to know my degrees of freedom. So my degrees of freedom are found by taking my sample size and subtracting 1. So my degrees of freedom here is 21. And this is really the only place that you're going to need that. Now to find my T critical value, I'm going to inverse T 0.02 and 21 degrees of freedom. You will get in your calculator a t-value of negative 2.1894, but because we're using this for a confidence interval, we're going to ignore the negative, so we will use a t-critical value of 2.1894. Similarly to that, if you have a 99% confidence interval, to find your area, 1 minus the 0.99 over 2 is going to give you an area of 0.005. Your degrees of freedom are your sample size minus 1, so 71 minus 1 gives us 70 degrees of freedom. And so for our t critical value, we're going to inverse t, our 0.005, 70 degrees of freedom, and you will get a value of negative 2.648. But again, we're constructing a confidence interval, so we're going to ignore the negative, and 2.648 for your t critical value. Okay, so that's going to become a really big important part of constructing our confidence intervals. So let's begin to talk about our confidence intervals. Okay, well, much like what we have been used to, we do have to check conditions for inference about a population mean, and they are the same, but the only one that is slightly different is our normal large sample. So this one is a sample means. That means that your central limit theorem can be applied. So the idea that if it's a large enough sample, it will be your population will be approximately normal. So you don't have to check your large counts condition necessarily. So you don't need 10 successes, 10 fails. You just need a sample of over 30. And then it's randomization, and the 10% condition also have to be met. Okay, so before we actually get into any actual calculations, which we'll do in the next video, let's talk about when we can safely use a t-critical value. So to estimate the average GPA of students at your school, you randomly select 50 students from your class, from classes you take. The histogram of the distribution is below. So as far as the distribution is concerned, it is symmetric, but the primary problem with this is within the sample. So we should not use a t-critical value here. So although the histogram is roughly symmetric with no outliers, the random sample of 50 students was only from your class and not from all students at your school. We should not use this data to construct a confidence interval. So perhaps a random sample, but not from the correct population. Okay, so how much force does it take to pull wood? The figure below is a stem plot of the force in pounds required to pull apart a random sample of 20 pieces of Douglas fir. Okay, so we would not use a t distribution for this one either. So the graph is strongly skewed to the left with possible low outliers. You can see it right here. So it's strongly skewed left with possible outliers. So we cannot trust that a critical value from a t distribution with degrees of freedom 19 would work for this. Okay. So suppose you want to estimate that the mean SAT math score at a large high school. The figure below is a box plot of the SAT math scores for a random sample of 20 students at the school. Okay, so this distribution is actually only moderately skewed to the right, and there are no outliers. And so this distribution would be ideal to use for a t distribution. In class, I'm going to talk more about the idea of the difference between strongly and moderately skewed, so that you kind of have a better idea of when to decide whether it's strongly or moderately, because you will not necessarily choose a t distribution if it is strongly skewed. Okay, and that's it for the second video. In the third video, we will start our confidence intervals.